Alright, time for another DraftPhysics.com, DebatePhysics.com, also video presentation. So, in line with more low-quality debating, where every single argument I have made is ignored, and these trolls just keep doing the same shit. Arguing as if they made an argument somewhere, and no, they haven't made any argument anywhere. Okay. I feel like you're avoiding our little debate about Newton. So he posts this on a video that's entirely about the double slit experiment. So it has absolutely nothing to do with 1/2 mv squared at all. The video. Couldn't care less. All right. That's how rude and obnoxious they are. Okay. I'm still curious. I'm still extremely curious. Do you admit that Newton's conservation of momentum is the same as in the mainstream? No, of course I don't agree. I think you're an idiot and you're preposterous. Your argument is preposterous. Nowhere in anything Newton wrote did he ever talk about making free momentum, like this is a real thing, you could make free momentum. Or did he ever use terminology, stating anything like mv squared. He never said velocity squared, never said the words. So you're full of shit. Okay, physics and completely disagrees with you. Same as mainstream physics and completely disagrees with you. So this is in the context of everybody got called a Newtonian, okay, while Newton was still alive. There were Newtonians. They hated the Leibnizians, and they argued these points. And then even after these two characters died, okay, there were still arguments about how mv squared is free energy. And the Leibnizians would argue the opposite, saying that Newtonian physics was free energy. Then they had this whole thing called the vis visa controversy for 100 fucking years. Okay, tons of people wrote about it. They had contests in France to resolve it. It was a real argument. The woman translating Newton into French, okay, he was a Leibnizian. Okay, and she, probably better than anyone else, should know whether Newton was a Leibnizian or not. So again, the whole thing is just such bullshit. Alright, the quotes in my previous comment should make it 100% clear. So there's no quotes in his previous comment. And we're actually finally done with you. Okay, so just fuck off. I've given you every chance to, he hasn't countered a single argument. So let's just go through a couple of them briefly to just point out how preposterous it is. And they're saying Newton didn't notice. I mean, that's their argument, that somehow Newton didn't notice that every single time, let's understand, every single time you ever have an interaction between a lighter mass and a heavier mass, or a heavy mass and a light mass, you will not conserve the kinetic energy in any case, ever. So it'll never obey the third law, ever. You'll never get an equal and opposite reaction. It won't happen. So in no circumstance, whether it's an explosion or whether it's a collision, it doesn't matter. You'll never get an equal and opposite reaction, and the gun proves it. No equal and opposite reaction in kinetic energy. 2,000 joules go with the bullet, and only 2 joules go with the gun. Why would Newton write a third law, equal and opposite reactions, or actions, if you can't acquire these equal and opposites unless they're exactly the same mass? If they're the same mass, then I can get equal and opposite. But that's the only case. Every single other case fails to produce equal and opposite. So, I mean, right there, there shouldn't be any argument. He wouldn't have written a third law if he believed in kinetic energy. Absolutely not. All right, and then this is the example where they're claiming Newton said this does happen. And I'm saying, well, it's subject to interpretation. I'll say that much because Newton wasn't very good at writing books, frankly. Good scientist, but shitty verbitist, okay? He wasn't very good. And the very fact that he's trying to describe things without drawings, and that's just the fact. The drawings in books back then, you had to have somebody carve it. It was, really expensive to have a drawing. So none of this is illustrated, and he's sitting here trying to, I have the advantage of this board, and I can explain how something might move. He didn't have any of those advantages, so he's trying to describe in words an event. And yes, he's not perfectly articulate. But the argument is that they're basically saying that Newton believed you could put 100 quantity of motion, that's what Newton used as a term, okay, into something, foot-pounds, and get 130 out. 50. Okay. I mean, it's free momentum in a direction. And they're saying that Newton wouldn't observe that, hey, that's really weird. I only put 100 bits of energy in, and I get 150 bits of energy going in the same direction. Well, why can't I just keep doing that again and again? Just keep making more and more energy. That's pretty cool, free momentum. So they're saying Newton couldn't figure that out. And then they're saying that Newton couldn't figure out that, this guy did, literally thousands of pendulum experiments. And so Newton couldn't figure out that if I did the pendulum in a little different way, where I just had a little feeder, okay, and say these were 6-pound objects and these were 1-pound objects, I could get a ratio something like 100 in, okay, so the same force in, 100, and I could knock the heavy ball out, okay, with nearly 200. Twice the energy. They're saying the more energy I put into the object, the more reflection I get. That's their actual theory, that I'm throwing something at a surface, and the more it bounces back, the more energy I put into the object. Now, is that your life experience? It's not my life experience. My life experience is, no, the more the surface yields, the less I'm getting back. So if I don't throw something like at a brick wall, I throw it at a piece of plywood that's kind of wobbly, I'm not going to get much back. Just a fact. And to get much back, I tend to usually have to use springs or some other device to create something like a trampoline. I have to create something that's very elastic, and it'll give me my energy right back. Not take any of it. Not go anywhere. The simple truth. And so again, it comes in with 100. I get 100 back again, and I can just do it over and over and over again. And I can just create maybe 10, 20, 30 times the amount of energy I started with. Momentum that I started with. And so Newton couldn't figure that out as the implications of 1/2 mv squared. That's the clear implications of 1/2 mv squared. So Newton also, thinking about objects in space, now he probably didn't think too much about spaceships, but he certainly knew enough about comets and trajectories and momentums and all of that. And, their basic argument, again, it's just the fact that people talk about gravity and they say things like, well, okay, you could be in space, all right, you want to move somewhere in space. Well, how do you do it? You have to basically have a piece of matter that you can get rid of, and that'll be essentially constitutes a thrust. And so if I throw 10 pounds or I throw 1 ounce, if I change how much velocity I throw them with, I can end up with the same this way. And the this way is only going to be dependent on the momentum. If I calculate the kinetic energy of the small object going fast, and it comes out to 2,000 joules, for example, the gun bullet, or I calculate it based on the recoiling gun, the 2 joules, okay, that won't decide how far I go. If I release the bullet to the universe, I'm not going to get 2,000 joules worth of momentum. I'm not going to get 2,000 joules worth of motion. I'm only going to get the 2 worth of momentum. And if I do the same with the gun recoil, that's all I'm going to get is equal to the gun recoil. I'm going to get 2 joules. I'm not going to get 1,000 times less because I'm 1,000 times bigger. I'm going to get the same momentum. The bullet has the same momentum as the gun recoil. The gun recoil has the same momentum as how much I'm going to move if that gun recoil is absorbed by me. And if it's an elephant, it's going to be the same momentum. There's not going to be a reduction in the energy because you transferred it to a larger object. Their theory is the larger the object and the slower it goes, the less energy it has. I mean, that's a glaring statement. And clearly, Newton was detailed about everything. You wouldn't talk about that huge detail? Come on, nonsense. So again, nobody believed Newton was a Leibnizian. No one. Okay? You can't show me anyone during those 100 years that said, oh, there's no argument because Newton is a Leibnizian. He believes in it. And they brought up arguments like the lever. So let's understand, it wasn't like they didn't have these arguments, and people brought up the simple argument that, well, if I do this crap on a lever, and I put a 4 mass here and I put a 1 mass here, those two things are going to balance. 4 units of distance, which means 4 units of velocity. So I'm going to have a 1 mass moving 4v will equal a 4 mass going 1v. Those two equal. I can't put the 1 mass here. That's what they're claiming. They're claiming that twice the velocity is the same. All I need is twice the velocity in a 1 mass object. And I will have the same force as 4 pounds going 1v. Doesn't happen. The lever will just swing right down this way and oscillate down here. It won't balance. So he didn't deal with any of these arguments, not a single one of them. So, there's just no point with these people. No point. All right, so I think that's enough. And I want to talk about photons. And I don't really want to do the charge argument, but I do want to do the photon argument. And because I have, it's a change, subtle, but it's a real change in understanding. So let's say you did have an electron inside of an atom, and you had another electron. Okay, so let's just say there's in different orbitals, or in some circumstance, there's 2 electrons in space that are, they have a pressure with each other. That is, they're repelling each other. So they have a force against each other. They're communicating through force. Okay, that's basically saying you can't get this close. Now the real argument is that what's really going to happen is there's going to be proton force that's going to go right through the electron, turn into electron force, and that's how they're going to hate each other, is because of the conversion of force. But the interesting part is the only force that can stick to them is their own kind of force, electron force. So the idea would be, is you could argue that, yes, the closer this one, say this one gets hit with some extra energy and it moves closer to this other electron, by the inverse square law, okay, the force, let's see how to draw that. The force is much stronger. Let's see how to do that. I mean, the idea is the force is much stronger, and it gets weaker and weaker and weaker the further away you go. And so what you're basically arguing is that you're plowing something into something that's going to keep trying to push it back. It's hitting it more and more and more. So the idea is the electron is going to get pushed by bits of energy that it's going to collect. And that's how it's going to gain momentum. And so if it comes in with momentum, all right, into another electron, okay, these little bits are right next to each other. That is, they could all leave almost instantaneously if I could hit another electron with the same amount of force. So if I have another electron with the same number of little bits, the argument would be is these 2 electrons, when they start interacting with each other's force in a major way, I guess I should draw it up here, both of them will start releasing the force bits, okay, and they'll be releasing them very close together. So all of those little force bits will leave, and all of these little force bits will leave as they get closer and closer to each other. Because the 2 objects are moving in, the speed of light force is still going this way, the proton force. It's going to create extra electron force between them. And every single time an electron force hits this way, it's going to reflect a bit that way. This bit will hit this one, reflect a bit that way, and they'll reflect all of the energy. And so what you're going to end up with is, say the field energy has an average distance of like this, you're going to end up with a hunk of that that's going to look like this. So that's sort of the difference between, you could argue, I could make that into an argument about infrared versus ultraviolet. But it's really not about this. It's about the fact that then there's big spaces, and then there's another instance of that tight force, and then a space where there's fewer, and then there's more tight again. And that is the frequency that we can measure. That's the one we can make tools to see. We can't make a tool that can see this. That can see the carrier frequency. So basically it's like FM signals or AM signals, which are basically doing is starting with I guess AM is the better example. Yeah, and you're just increasing and decreasing I guess it's modulated FM would be the closer example. So you're just taking basically a carrier signal and you're changing its frequency. And the changes in its frequency, okay, the amount of it, is the Morse code you're sending. So you have a signal that's on a frequency and you're changing the frequency. So it's like 50 megahertz, then 100 megahertz, then 50, then 100, then 50, 100, that kind of idea. And that's your signal, is the compression and then expansion, then compression, then expansion, then compression. All right. So, yeah, and so it's when this hits an electron, obviously it gives it, because it's so tight, the little bits are hitting so quickly that it almost instantly gives the electron a very high speed. And so now the electron can travel a pretty far distance before it starts dragging into the inevitable extra energy it's going to crash into, because it's going a very fast speed. But it has some durability based on how much of that stuff is hitting it, how much of that compression hits it. So it gets up to a very high speed, can travel further because of the higher speed. Yeah. And every time it interacts with another electron, it's going to do the same thing. Every time an electron collects, so an electron can collect energy. This is the real, it's kind of the key argument, but it's so nuanced, that I'm not going to be able to do it justice, because it's just so nuanced. Okay, but the basic idea is an electron can collect one bit of energy. Okay, so there could be bits of energy hitting it at some time interval that's kind of large. And so it gets hit with a bit, and then it doesn't get any opposing force, and it gets hit with another bit and another bit. So it could collect energy that was coming over a very large period of time, and it's going to reduce it to energy that's going to be released in a very short period of time. So it's going to take in energy that hit it little bits at a little incremental added energy, and it's going to release it all as one clump of energy in a very short period of time. So that's what electrons are constantly doing. So every time you move an electron, okay, it's basically going to take energy in terms of creating a motion. And when it creates the motion's not going to be, it's going to be either really fast and then it slows down, or it's going to be slow and it speeds up. Okay, but when it hits something, another electron's field, it's going to release that energy quickly. Yeah. All right, so I think that's the core argument, and it's just trying to explain, how that's what affects the creation of, say, Earth's heat, is that it's not heat going in. Okay, so what you have, we can't measure the actual heat of the unit. I mean, anything, because we can't measure the actual force that's doing the work. We can only measure stuff that has the frequency. So it's kind of like a magnet, right? Something magnetic can see the power of a magnet, but if it's not magnetic, it doesn't see anything. It has no urge to move in or urge to move out or do anything. And yet all I have to do is change that property. I just make it so it can see and all of a sudden it'll dramatically move. And so that's the trick, is that we can't see it. We don't have a tester that can see the field energy because everything's being hit by it. So the Earth gets hit by the little bits, and what happens is as it pushes the electrons, it starts making it into a frequency. So as it travels through the Earth, it's pushing on electrons, and the electrons are basically herky-jerkying, and every time they do that, they send a signal both ways of compression and expansion, and compression and expansion. So they're sending the Morse code as the electrons push into the field, lose the energy, push into the field, lose the energy, push into the field. And so it turns into heat by the time it gets through the Earth. And obviously the center is going to be a place where a whole bunch of these electrons go through. And so per unit of atoms, per number of atoms, there's going to be more action in the center than there is in the bigger and bigger shields of matter. So you're basically arguing that the energy comes in out here, and the simple argument is it's basically just going to get funneled into here. You know, that it doesn't, it's going to be this much surface here is huge. The amount of atoms here is tiny by comparison. So obviously it's the same energy in a much smaller area, and so it's going to be much hotter. And as it dissipates out, you're just saying it's 4,000 degrees in the center, say Celsius, something like that. And, you know, by the time it gets to the surface, you know, it's minus 200 degrees Celsius. Or something like, whatever, 200 degrees Kelvin. It doesn't sound like a lot of heat, but it's a lot of heat when it's spread over that giant surface, that giant density of matter by comparison. If you just took it, you know, like I said, if you said, here's 10% of the Earth's mass in the center, and then you have 90% on the outside, I'm just saying, yeah, it's obvious that, you know, diluting something by 10%, I mean, diluting it 1 in 10, you know, it's a huge dilution. All right. Don't hate that, but all right, back. So let's talk about polarization. Just thinking about different experiments and different ways to test it. And so the basic argument is let's just say electrons, when they move because of some cause like electricity, you know, where you're shoving an extra electron into an atom, and so basically would argue that, you know, the atom has a shape, and then if you're pushing an electron in, it changes its shape, so it, you know, can't go this way, so it goes this way. So if you push in this way with an electron, the electrons over here are likely to go out, and this one can't go this way, so this one goes that way. And so every time that happens, it involves this reflecting of a force bits, because it's trying to go this way and it's getting pushed that way, which means it's going to reflect whatever energy it has pushing it in. And so that's where you get these clumps of stuff. And the idea is that's not a photon, it's just a piece, a clump. And these clumps can be in all kinds of different arrangements, flying through space at all kinds of different angles based on electrons being moved in and out. So there's a ton of this stuff. And this stuff only is a photon when it hits a surface in a manner that's going to duplicate what caused it, essentially. So you're kind of saying it has to be duplicating it in the sense of creating some kind of electricity, or this ability to push an electron into another atom. So I would argue the frequency is something like, well, that's too close together. Probably a bit better if I just use 3 little clumps. And then there's a distance in 3, and then there's a distance in 3. Could be just 2 because of this more complex way you're making a photon. It's probably less likely that it's going to happen. where it can hit some surface. So the idea is it's flying at the speed of light, these little bits in this higher density, and they're going to hit a surface in that higher density and push on an electron and make it go further because it's more energy than just one little bit. And so the idea is it hits an atom and it causes that atom to push on the other atoms, which means push on the other electrons, okay, and that'll be a cascade. And the idea will be is that if you push on this atom from this angle and this hits and also pushes on it, it's going to give this electron even more momentum. And then you hit it a third time and you give it enough momentum to knock it into the next atom, or it has enough momentum to hit the electron out of the atom and push it into another atom. Now, if you do it with enough energy, you push the electron right off the surface. So if it's not enough energy to push it off the surface, you have electricity. And if it's enough energy to push it off the surface, then you have, an electron emitter, presumably. All right, so this would be the redraw of the idea, is that you have a row of atoms and you have a row of atoms on another surface. So this could be like for a radio kind of idea, and you're sending the electricity in here, okay, and you're basically going to be sending it with a frequency, okay, so it's going to push and then not push and then push and then not push. Let's see how to describe that. Yeah, so there'll be this will be the gap it's creating, okay, is this gap where there's as it pushes, then the rest of the electrons can relax, and then they're pushed again, and then they excrete the pattern. And this polarization, for most things, this is going to be equal to the frequency. So in most cases, there's a clear relationship anyway between how long the antenna needs to be and the frequency that you're going to project with that antenna. And so it's clear that there's a connection between the polarization and the frequency. So the higher the frequency, the narrower the light, in terms of its size, and the bigger the frequency, the bigger it is. So that's why microwaves can be blocked by holes. You could have half-inch holes will work. They make them smaller just because smaller is even safer, but clearly bigger holes would work in terms of breaking the microwaves, in terms of knocking all three things can't get through, so the pieces only get through. And so that's sort of the argument, that they just become part of a field of a whole bunch of pieces, and it's just about reconstructing those pieces on a surface, and there's circumstances where you can reconstruct the pieces and have a photon. So technically you could have a piece of microwave. Instead of duplicating this, arriving at a surface, you could have a piece come from here, hit that, duplicating this timing, and one coming from over here, duplicating this timing, and so you can make a photon out of pieces of photon. A simple argument. And that's basically what the double slit is doing. It's breaking all of the photons that go near the surfaces are getting broken into pieces, in the sense that this coherency is getting lost, and they'll be sent in different directions, and there are different directions in all a horizontal plane, and so you're sending them in that horizontal plane, and you have some sort of odds of putting a photon back together again if you create the right distance between a photon hitting one surface and then one hitting this other surface and traveling the longer distance and showing up at the right time to hit the surface, to basically just duplicate what caused it, which was electricity pushing on atoms, pushing on electrons, and then you're just going to reduplicate the same effect in the surface by causing the atom to pressurize. It's going to cascade that pressure into the next atom and then the next atom, and get enough energy to keep that going. So that's part of the photoelectric effect, is just creating electricity, which it does at a lot lower frequencies. Frankly, radio waves are kind of proving it. It does it at almost any frequency. All right, so let's see where else I can take this. I mean, so the important point is that, you know, physics is saying that that a single electron could somehow be hit by a photon and create a photon. You know, that somehow this big giant thing that's, let's say it's 500 nanometer light, you could argue that the polarization has to be something, at least 250 nanometers. So let's say it was only half of the frequency. It's still going to be monstrous compared to the average atom that's only 5 nanometers. So you're saying the average atom is 5 nanometers. I got at least, 25 of them in there. More than 25. 12, whatever it is. 5 into 25. Now that shouldn't be that hard, Gary. Come on. You can do it. 50. So 50 atoms worth. The polarization is 50 atoms high, so size-wise. So how could one electron inside of an atom create a photon or absorb a photon when the photon is, spread over such a huge area? So it'd be nice to come up with an experiment that proves that. Now, obviously, the small aperture proves it in the sense that, there's a certain point where none of the light, the aperture is smaller than the polarization of all the light you put in. And so you're guaranteed to just pretty much have fringes. The problem is that you can have fringes both ways. So, having this round surface, I can put it there. You can understand that it can take two pieces of light and say, okay, one piece comes from here and one piece comes from here. All right, and you can do that two ways. They go in or they go out like that. So that's the problem, is that you'll fill in, okay, the place where it'd be nice if you could make a small aperture and then prove that it casts no light here, that it'd be black here, and then it would get light as you go further out. But you can't do that experiment because of the fact that you'll get pieces from this piece and this piece that'll go into the center and create light in the center. So it'll fill it in. So there'll still be some visible light projected onto the screen, even though you made an aperture that's smaller than for any photon to get through. It's still going to create fringes going that way, and it's going to create fringes going this way. So you're still going to get light on the other surface. But it's going to be ringed, and it's going to be a lot of things that'll be sort of a giveaway. So the other thing I was just thinking of is the shadow argument. If you put an impediment, okay, and you have a light source, and it makes a shadow, it really depends on how close that surface is. So if the surface is really close, I get a hard shadow, a pretty dark shadow. But if I move the surface further away, the shadow disappears, and it's essentially because there's only a certain angle that this light can be bent at. All right, so it's a very slight angle, and so it only crosses this middle line because of the slightness of the angle. All right, it only crosses the middle line at a certain distance. So at the tight distances, it's not enough of an angle of bending. It's not bending the light enough to fill in the shadow. But the further away it is, then that slight angle bend now can fill in the part that was a shadow. And it seems that, okay, so the explanation for water waves does essentially the same thing to some extent, but you have to sort of understand that it's not in the same proportions. I guess I would argue that a pin or a needle in water is going to be filled in right away, and it's not going to have almost any shadow at all. But you could argue that's because of the gigantic wavelength. But again, when water goes around a surface, the real trick is that the calm water behind it is obviously as the water pressure on the surface is pushed up into gravity, there's pressure pushing it back down, and so it fills in this way and this way because there's no water pressure where the shadow is. So it just fills in the shadow because there's no water pressure there. So that's the problem with that. It's way too, this is a medium and there is no medium here, so that's the difference. These are rays and vectors, and this stuff is a medium, water. So it doesn't make for a very good comparison. Now the other experiment I thought of that would be something, physics should really try, is polarizing filters. And then I was thinking about just regular double slit experiments too. I mean, they always do these experiments with the filters, pretty close to each other. And it'd be interesting to see is if you separate these filters by a great distance. Okay, so if you move the other filter very far away, does it still have the same effect? Because I would argue, especially in the case of using wires as a filter, as a polarizer. So you can use little thin wires, okay, really close to each other, and that will be a polarizing filter for visible light. So it is possible to do it with wires instead of the plastic film that everybody uses because it's more efficient. And the thing that wires are going to do is obviously they're going to do that thing the needle's doing with the shadow. It's going to bend light in all these directions. And so when the light goes through the polarizer, these bits are going to hit electrons. I guess I should have explained that part. I mean, electrons are bouncing in and out of a surface, and they have little bits of energy when they do that. So when it's going into the surface, it has little bits of energy going this way. And basically I'm saying when the photon bit hits, the little concentrated bit of energy, those two are added to each other and an electron moves this way, which means, okay, when it moves that way, when it slows down, when it gets stopped, it's going to release the energy in this direction. And when it's pushing into the field, reflecting, that is, as it's gaining velocity, it's going to reflect energy in this direction. So it makes the photon, obviously when I push this way with an electron, I've expanded the space behind it. And when it goes back, it's going to be pushing on the space going that way. And so, but at any rate, the point is you're going to combine these two vectors, and the way the energy is going to go is this way and this way. All right. Now, I don't know if you could detect that part when the photons go in very coherent and they come out as a reflection. So you can often see that with these experiments. If you put a detector behind the laser, you'll also see a pattern that's a reflected pattern off of the slits. I think that was most apparent when I was doing the interferometer type experiments where you're using glass, a plain piece of glass as a beam splitter. You can get it so you get a pattern going both ways. You get a reflected pattern and a forward pattern, indicating that this is more complicated than they're arguing. So anyway, the whole point of me pointing out that you could make the polarizers and just see if you can, because the idea would be is the further away it would mean that most all of the photons would end up, because of the bigger angle, would end up missing the second polarizer, and you wouldn't be able to fix them again. So you wouldn't be able to put an in-between filter in and fix any of the photons because they'd be too far away. That means they'd all miss the the ones that were broken wouldn't be able to be reconstructed because they would already have traveled too far. And the way it works is if the polarizers are close to each other, the little bit of angle change isn't much. Over a short distance, it's only a tiny amount. Over a long distance, that angle has made a huge separation. And I think that would make a difference. So this might be an experiment I can do. I have some polarizing film. I don't know if I have enough, but I know I have some somewhere, so I have to find it first. I don't know how high quality it is either, and I hate to cut it, but whatever. It shouldn't be that big a deal. But yeah, it would be interesting to see if the polarizer, if it is actually works better the closer the films are to each other versus the further away they are, how much that changes the effect. So that also has me thinking about the whole way of doing the single type photon experiment with a light source, where instead of putting smoky glass in front of it to diminish it, you just make sure you put it very far away from your slit experiment. And that is an interesting variation on the theme. And part of me says it also gives you the opportunity to do an experiment where you could put photographic film and just, let it 3 seconds worth of light at a far away distance, and you get a certain number of photons that'll hit this surface from the source. Right, it has to be an absolutely dark room. And you could measure that on a photographic paper, and then just use the photographic paper and put your slits in the paper, the photographic film or slide, or however you want to, whatever you're using, the photographic medium, and then have another piece of photographic medium in it behind, and then see how many photons hit this medium and this total, and see if that equals what actually hit this original surface when no slits were there, and see if this plus this actually equals this. And that'll tell you if the photons are actually being destroyed in some way, or whether you're retaining them. And I would argue that there's a lot less light with the slits, because you are breaking the photons and you don't remake all of them, put simply. Alright, let me think if there's anything else. Alright, just thinking about the polarizer argument. And I guess the point should be made that the two types of polarizers are very different. So if you use wires, there's obviously a physical impediment that's going to destroy some percentage of the light. And then you have the idea that you're bending it, over these surfaces, and that's what's causing the photon to be incoherent, let's say. But in the case of the plastic type, that's just two surfaces. So you're just changing the phase of part of the light. So what you just have is, instead of, you have two surfaces, two thicknesses versus one thickness, and so one surface gives you a 90-degree change, and then the second surface is 180 degrees. And in the phase, and so it's basically just slowing. It takes longer for the light to get through the surface, so you're changing the phase of the arrival time. So you're changing the one that goes through is going to be slowed down, so you end up putting it in the wrong location. So you lose this timing thing, and you end up with an incoherent frequency because of the fact that you've taken one segment of the pattern and taken it out of phase. And so then you can understand why you can reconstruct that, because you just have it go through another filter where you hit the part that was 90 degrees shifted, and you shift it again another 90 degrees, and it's back in phase, that kind of thing. So just should make that distinction, that when I'm talking about separating the filters, I guess it won't make any difference if it's the plastic type, because you're not causing the light to be bent as much as you are in the case. I mean, still going to get bent on these surfaces. They're these are real surfaces for the second layer, so I imagine it's still going to cause some bending. But I guess I wouldn't know until you actually try it. So I guess that's what I have to do someday. Anyway. Yeah, maybe you got to do it with some other kind. Maybe infrared. Yeah, that's an idea. Yeah. I don't know what the distance would be for a filter, a polarizer for infrared light. So, you know, you got like a 1 centimeter for radar, and you know, microwaves. Maybe for infrared light, the distance would have to be smaller, but you know, it wouldn't be as small as for visible light, so there would be some advantage to that. Well, anyway, I have to think about it. It might be worth testing. And such. Yeah, creating different infrared filters. Yeah. And, you know, it gets complicated because, you know, it's interesting how different materials like wax can be used to make a lens for microwaves, which is just sort of, you wouldn't think so. Yeah, but it works. All right, so enough of that. Yeah, maybe I'll just say that's enough for this video. So there's a lot of stuff I haven't, you know, in the draft form still. But the basic idea that, look, particles win, it answers all the questions when it comes to photons, and it's just figuring out the nuance of the interaction between the energy quanta and the electrons, and the fact that it's really just about the motion of the electrons and the pattern created by the motion. And yeah, and the rest is just details. So till the next time, and such and so forth and whatnot.